Welcome everybody to another session from Nairo Research. I'm Srijit here, and today in this session I'm going to brief you about an intro on DFTB from AMS family. So, speaking about DFTB or density function type binding, it offers a computationally efficient approach to approximate the density function theory calculation, making it a little bit suitable for studying larger systems and longer timescales than full DFT. So it retains a quantum mechanical description of electronic structure but employs several key approximations to reduce computational cost. So at the core, DFTB starts with a second order Taylor expansion of the DFT energy function around a reference density. So this theoretical concept, we will look into it a little bit brief later. So this leads to a Hamiltonian that depends on the pre-calculated parameters derived from DFT calculations on isolated atoms and dimers. So these parameters typically include on-site energies and interatomic integrals that describe the electronic interactions between atoms as a function of distance. So this typical example which you are seeing is I have taken for a potential energy surface scan. And under this example, I have selected two carbon atoms and I have adjusted the distance between these two bonds. So the result I will show you a little bit later. And also in this AMS, it is implemented within the suite, which provides a user-friendly interface and a robust platform for performing calculations on molecule surfaces and bulk materials. AMS DFTB or DFTB often includes various extensions and improvements to the basic DFTB methods, such as a different parameterization, dispersion correction, and solvent models, enhancing its accuracy and applicability to a wider range of chemical systems, which makes it a valuable tool for tasks like potential energy surface scan, optimization, molecular dynamics simulations, electronic structural analysis, property prediction. For systems with full DFT would be computationally prohibitive. And speaking about the foundation, it lies in a clever approximation of the total DFT energy, which can imagine starting with the exact DFT energy expression, which simplifies this by performing the second order Taylor expansion of the energy with respect to the electron density. So this seemingly is a small step which has profound consequences, which leads to a Hamiltonian or the operator that describes the energy of the electrons that can be constructed using a pre-calculated parameter. And these parameters are typically derived from the prior, more rigorous DFT calculations on isolated atoms and even diatomic molecules. So they can encapsulate the following information about on-site atomic energies and how atoms interact electronically as a function of their distance, and the type of atoms involved by pre-calculating and storing these interactions. So DFTB avoids the computationally expensive self-consistent field in iterations that are central to full DFT for the core electrons. And also, it provides a valuable user-friendly environment for setting up, running, and analyzing calculations in our AMS environment. Beyond the basic DFT formulation, it can incorporate enhancements to improve the accuracy and applicability. Furthermore, it can be seamlessly integrated with other AMS modules. So we can focus on various calculations covering up with band, ADF, ReaxFF, etc. So speed and scalability, speaking about the core advantages, the ability to tackle larger systems and long simulations even on standard hardware is a major draw. And also the balance between the computational cost and the quality of the results achieved through pre-calculated parameters, handling different interactions, and also the versatility for different dimensionalities, the ability to handle molecular as well as periodic systems, make it a true versatile tool for a wide range of materials. So the pre-optimization powerhouse, which can be a fast pre-optimizer for more computationally intensive full DFT calculations with AMS, ADF, and band underscores its practical utility in multi-scale modeling workflow. And also we have one more semi-empirical methodology which is known as MOPAC. So this bundle of semi-empirical library with the DFTB significantly increases the value of proportion. So offering an even faster alternative which needed. and integration of advanced methods like this Professor Gramme's GFN1 XTB method with its broad elemental coverage enhances the accuracy and applicability of DFT module, which we will discuss in the coming videos. So this is actually an example, or sorry, this is actually the introduction about the DFTB. So this is actually the model which I have just mentioned. So each and everything which will be briefed in the coming videos. So for right now, I have given you an example of a small cyclohexene where we can check that how the bond breaking is happening using a potential energy surface scan. And officially, this will be the outcome of that calculation. So you can see that how that bond breaking and bond formation. So in the coming videos, I will be briefing it more with scientific examples that how we can implement DFTB with other modules. So right now I'm winding up. Thank you. And for more information, I request you to subscribe our YouTube channel, Narrow Research India, as well as our page in LinkedIn. So thank you.